In this video, we're going to talk about specifically surface frictional force and how you can actually solve for it based on the surface. So each surface will have a different amount of friction. You definitely know this if you've ever tried to move furniture. Whenever you're thinking about a hardwood surface versus a carpet, you definitely know there's a very big difference in how furniture moves on those two surfaces. So what affects surface friction? Well, first, the weight of the object. So a more massive object has more friction. So it is much easier to push a very light object across any kind of surface than it would be to push a really massive object around any kind of surface. The other thing is the surface itself. The rougher the surface is, the more friction you experience. Carpet is much harder to push something on than hardwoods. And that's because the rougher surface of carpet creates a higher amount of friction than the smoother hardwood surface does. So how would we use these two factors in an equation for friction? Looks like this. So first of all, don't freak out with these whole like little symbols that look really strange. It's really not that bad. So first of all, we've seen F of F, right? So F of F is the frictional force. So that's frictional force. This is the normal force. And on the horizontal surface, it equals the weight. Okay, so on a horizontal surface, the normal force is equal to the weight. Now, the reason why we can't say weight here is because whenever you get to an incline, the normal force is actually lower. Because, you know, anything that's on an incline is much easier to move than on a horizontal surface. You know, if you're trying to push it down an incline, it's a whole lot easier than trying to push it across a horizontal surface. And that's because the weight isn't different. The weight's the same. What's different is this normal force. So as you increase your angle on a surface, then the normal force will decrease. But that's as much as we're going into that. This mu, the mu is the coefficient of friction. And this is how we take into account the surface. So Fn takes into account the mass and the weight of the object. The mu takes into account the surface. So carpet will have a greater mu than hardwoods. So hardwoods would have a smaller mu. And mu is just a Greek letter. It's an M, a lowercase m in Greek, so mu. It just looks like a U with a little tail, or I guess a beard, whatever way you want to look at it. So no freaking out over strange letters, it's just a mu. There are actually two types of these coefficients. So the coefficient of static friction, so static characters are those that don't move or don't change in literature. And so the mu s, or the static coefficient, is the coefficient before motion. The kinetic, so kinetic, the word kinetic means moving. And so kinetic coefficients are during motion. So static is when it's sitting still before it moves. Kinetic is moving, so it's during motion. Now, if we go back to, say, our demonstration we had in the hallway with the wagon, anyone who was pulling knows this answer. Is it easier to get an object moving or to keep it moving? Well, anyone who was watching and anyone who was pulling knows that it takes more force to get an object moving than to keep it moving. So static coefficients are larger. Static coefficients are larger because it takes more to get it going. You can think back to the idea of inertia. In order to get an object moving, you have to go against its inertia. Inertia is just the tendency for an object to keep doing what it's doing. Well, if it's sitting still, it doesn't want to move. So you have to force it to move. So not only are you trying to go against this this surface, you're trying to go against the weight, but you're also trying to go against that inertia. So static is larger. For kinetic, it takes a lot less to keep it moving. So this is smaller. The reason why, another reason is if you, again, think back to inertia, once an object is moving, it wants to keep moving. And so whenever you're pushing with a force, yes, you're still pushing against friction, but the object wants to keep moving. So it doesn't take as much force to keep it moving. So static is larger, kinetic is smaller. Anyone who's pushed a car also knows this. It's harder to get the car rolling than it is to keep it rolling. So what we're going to do now is just do some examples that you might see. So the first is asking what force is required to start moving the object. So since it's initially sitting still, so initially still, okay. So it's not moving initially, we have to force it to move. So this is static. So we're asking what is the static frictional force? So the best way to do this, start with a free body diagram. Start with the box. Inside the box goes the mass, which is 30 kilograms, 30 kilogram mass. This is on a surface. Let's make sure we draw it on a surface. And now to kind of give you a little extra something to write down, of course we've got our coefficient. I actually write that right next to the surface because it is a characteristic of the surface. So mu s is 0.525, which goes with the surface. We of course have weight pulling us down. We have the normal force pulling back up from the surface. So we can find those as well. So Fw equals mg. So initially this should look really familiar. So 30 times 9.8, which is 294 newtons. And since we're on a horizontal surface, our normal force will also be 294 newtons. So equal and opposite for a horizontal surface. So now we're not given the frictional force, but we are given the coefficient of friction. So let's go ahead and put our arrow for frictional force. And let's see if we can solve for that. So that would be our new equation that we just found. Ff equals mu, and since it's static, it'd be mu s times Fn. And so our mu is 0.525. The normal force, 294. And so the frictional force will be 154.35 newtons. Now, this is how much force you have to overcome to get it to start moving. This is how much friction this object experiences. So if you push with less than this amount, so say 50 or 100, it won't move. And so anyone who's tried to push a car by themselves, you know this. You know you're just sitting there and you're pushing and pushing and nothing happens. You could think of, you know, the classic cartoon where there's like some object that a cartoon character is trying to push and you just see their legs just kicking around because they can't get it moving. That's because they cannot overcome this amount of force. Now, once you hit this exact number or greater, the object will start moving. So whatever the static frictional force is the minimum force required to start it moving. Once you get to this number, then it'll start moving. You can keep it moving a whole lot easier. So now let's look at that. So let's say you were able to push with that amount of force. Well, now initially it's going to accelerate because it's going from a stopped position to a moving position. So we want to know what is that acceleration whenever it first starts moving. So if you push the object with the initial static force, what acceleration does the object experience when it's moving? So initially, once it starts moving, what acceleration does it see? Well, let's start again with our free body diagram. So there's our box, we have our surface, and we know a lot of these arrows already. And so I'm just going to draw them in and then fill in the amounts. Okay. So we definitely know the mass. It's still 30 kilograms. That doesn't change whether it's moving or not. We know its weight. That also doesn't change. 294. Normal force is still the same. That also does not change. And it says you're pushing with the initial static. So the applied force is equal to that initial static friction because you push with just enough force to get it moving. So that was 154.35. Now, since it's moving, the kinetic coefficient is different. Notice it's a smaller value, and that's because once an object is moving, it's easier to keep it moving. So kinetic is less than static. So we'll put that here on our surface. So mu k is 0.325. Notice there's no units. This is one of the few numbers the entire year that will not have a unit. And so first thing we need to do is find our frictional force. Now, since our coefficient has changed, the frictional force is not this value anymore. So we need to find it. Mu k Fn, and so we have 0.325 times the normal force, which is 294, and we get 95.55 newtons. And so you can see this is much less than that initial force we needed to get it moving. So this is now our kinetic friction. This is our applied force. So frictional force, applied force. And notice now they're not equal, right? And so to solve, we do exactly what we did before. These two cancel out. These two do not. So F net is equal to the 154.55 minus 95.55, which gives us a net force, 35, sorry, 154.35, and so we get a net force of 58.8 newtons. So not zero, right? So net force is this, and then we use our net force equation to find the acceleration. So 58.8 equals 30 times A, so we divide by 30, and we get an acceleration of 1.96 meters per second squared. So not a very large acceleration, but still an acceleration. So this would be whenever you initially got that cart moving, you know, the little wagon, you would see it initially started speeding up, and then they were starting to push with a constant velocity. But initially they were pushing at a certain force that was equal to that static friction, but now since it's moving, the frictional force is less. So to solve these types of problems, you start with the free body diagram, mass, weight, normal. Then you find your frictional force using the normal, our new equation. Then you find the net force using your two forces. Then with the F net, You find the F-net equation to find acceleration, and you're done. I know it's a lot of steps. It's all about practice, practice. So the last type of problem you might see is what force is required to keep it moving, and notice it says at a constant velocity. So again, constant velocity means acceleration is 0. So that means all of our forces are going to be balanced. So all forces balanced. And so if we look at our free body diagram, put our surface, so this doesn't mean that there are no forces affecting it. It just means that all of the forces are perfectly counteracting each other. So we once again, we know the mass, which is 30 kilograms. We know the weight, which is still 294 newtons. We know the normal is still 294 newtons. And since it's moving, it's going a constant velocity, it's moving, so we know the frictional force is that 95.55 newtons. And so the question is, what force is required to keep it going at constant velocity? Well, since all forces have to be balanced for this to happen, then that means these two have to balance and these two have to balance. And so the applied will be equal to the kinetic. All right, so I know we just did a whole lot, so let's just go back and review really quickly. So you have your equation, your new equation to finding frictional force. There are two types of mu's, two types of coefficients. Static, from when it's sitting still, kinetic, from when it's moving. You have to push with a certain amount of force to get it moving. That force is equal to the static frictional force, which is larger. It takes more force to get it moving than to keep it moving. So notice it went from 154.35 to 95.55. So lower kinetic than static. Whenever you first start getting it moving, it is accelerating. So you are initially pushing with the amount of force required to get it moving, which was the static. It now has a different frictional force. So you have an unbalanced force creating an F net. Use that to find acceleration. Once it's moving, and you are now pushing at constant velocity, now the friction and the applied are equal. So initially it's not moving. Let's see, here we go. So not moving, push with at least static. So push with at least the static frictional force. Starting moving, you're still pushing with the static frictional force, but now it has the kinetic frictional force. Kinetic frictional force. And then once it's moving at constant velocity, you are now pushing with the kinetic. There we go. So when it's not moving, you're pushing with at least the static. When it starts moving, you're still probably pushing with the static, but now you have kinetic friction. And once you get to that constant velocity, now you are pushing with kinetic frictional force.